our fourth topic today, and this is 3D data analysis and interrogation. This presentation will be provided by Marco Vaquera, our principal application engineer, and he will be using the 3D Analyzer tool to display the agenda items. But it is also worth noting that these tools and features are also available in 3D Evolution, which is another software provided by CoreTechnologie. So I will give it over to Marco.
Thank you, Michael. Okay, I'm going to start sharing my screen. So as Michael said, and this is 3D Analyzer. So for those of you who have been following us during this morning presentations, you notice that I've used 3D Evolution up till now. This is 3D Analyzer, and the main difference is that while 3D Evolution allows you to change the geometry and save it back, 3D Analyzer is mostly what its name implies. It's a tool to analyze the data. You can interrogate the data at several different levels, and as you're going to see, some of the things that we can do is check the thickness of the walls, check for backlash, graph and undercuts, advanced analysis of the geometry. We can also do model comparison, collision detections, and one of the formats that we can do with 3D Analyzer, we can convert to is 3D PDF. So as well as 3D Evolution, it does handle the same, all of those formats that 3D Evolution can do. And as an example, I'm gonna show you some of those. So I went before through the file open exercise of showing you the CAD files under this drop down. And what I'm gonna do now is show you how this load up. And they don't have to be on the same format. As you're gonna see, just by dragging one of these into the window, it's gonna open it up. You don't need to specify the source format. It will automatically detect it and apply the correct filters. So this is a CATIA V5. We also have JT, and if you drag it on the same window, you can actually begin to assemble a product out of different parts in different formats. They don't even have to be on the same format. So that means that each one of these parts could be built by a different company or a different supplier. And in the end, you are combining a CATIA V5, a JT part, a Creo part, maybe a step file as well. You're beginning to build your assembly here. Maybe one of your suppliers works in SolidWorks. That's no problem. Maybe Creo as well. So we got an assembly made up of how many? 5, 6 different formats, which could represent 6 different suppliers or vendors. And that's not a problem for 3D Evolution, where you can build your assembly and then again convert this to anything that you want. Well, that would be with 3D Evolution, and here is mostly for checking the fitness between each part and the others. And something that I did in order for this to end up in the correct location, since now I'm building this assembly with the parts that have been provided independently, I had to convert these parts to absolute positioning. That's something that you do with the tool called assembly conversion in 3D Evolution. And I touched a bit on this before on one of the first presentations. So this allows you to take the part out of their context in their assembly and then put them back and then rebuilding with anything else that you want. So that's part of what I did. So this could end up looking like this with different parts that came up from whole different systems that have no relationship between them. So that's kind of the kind of things that you can do when you are combining these tools. So you see how we can open all of these files formats. And I like to touch as well on the switches again that change the way that the files are open. So you can choose to load PMI or not, which is product manufacturing information. So these are like the 3D nodes that you see floating around in 3D space, pointing to the different features associated with the datums, and then sometimes also specifying lengths and diameters. And you can choose to only load the structure itself. So that means that no geometry will get loaded at this point, but you can load it dynamically as you go. So if you have a very big assembly and you're only interested in part of it, like it's typical with airplanes manufacturing or design companies where they separate the plane by bullheads, you might want to just look at the back part of the plane would be the very far back bullheads. You can do that and then only work on that, and you'll be assured that everything that you do will be in the correct relative positioning, and you don't have to load the whole plane or a chip for that matter. Uh, Hidden objects, those as well are reference geometry that is created by the designers in order to have a reference frame for placing the geometry. So when you are converting this to a different format, usually you don't want or you don't need those objects. So you have the option to leave them behind, which will only weigh down your parts. And usually you're not going to need them because once you convert, you typically do not go and redesign the part. You work on the native one. So usually we leave this turned off. And so these are modified for the information that gets loaded. But the one over here changed the way that the data is loaded. So if you are in geometry mode, you're only going to get B-reps, which is just solid bodies, but there is no smarts or no construction geometry behind them, as opposed to feature mode. In feature mode, if the file is really a feature-based model, which means that it was built in a native system and then it retains all of the history, like the sketches, the relationships between different parts, if it's an assembly, all of the features that make up the geometry, patterns, holes, sweeps, splines, all of that will be retained. So if you choose this mode, it will be loaded up as such, and you will see the history in here. Instead of just being a single icon representing the body, you see each one of the operations. And that will be a prerequisite for 3D evolution in order to convert to another format in feature-based mode. That's another switch that we have. And then in representation mode, so some formats have a dual intent. So they might have the B-rep inside, but they also carry with it a lightweight representation. So in those cases, you can choose to only open the lightweight representation, and that will also save you time and memory. So if you don't need to have the full solid bodies of every part, if you just need it for like maybe a market ready geometry or AR/VR applications, or you just need a quick review of the part, you can choose representation, and that will give you a quick and light version of the part. So that's with the advanced viewing. I'm going to show you how you can convert as well to 3D PDF. So that's one of the few conversion options available in Analyzer, because remember, Analyzer is not really meant to convert. So in this case, you don't need to do a conversion like you do with 3D Evolution. It will do so automatically. So you just need to select that 3D PDF format, then save it, and that's it. Now I'm gonna find it again and bring it back. Sorry, I got that wrong thing. Oh, no, no, I cannot just bring it back a PDF, sorry. You gotta open up in the Acrobat. And this is just Acrobat giving me a hard time. Let me just make sure that I open it up with Acrobat instead of the browser. Here we go. So all of the geometries there, remember, each one of these parts came from a different supplier and a different CAD system, but here they are together and working in the same assembly in a very lightweight document, which is the PDF, 92 kilobytes. So if we just make the sum of the original parts that make it up, you can see this is 1.4 megabytes as opposed to 92 kilobytes. So this is a very efficient way to share information, and it also has the advantage that since it's not a BREP, and it's very is there is no straightforward way to extract geometry out of a 3D PDF. So this is also a safe way to share information across. So at this point, Michael, are there any questions?
None so far. We can move forward.
Okay, perfect. Okay, so our next topic in the analysis workbench is the wall thickness checker. So I'm going to jump back into 3D evolution. Then going into our analyze workbench here, we're going to go into our thickness checker. But first, I'm gonna load up a proper model for this. So if you've been into any of our previous webinars, you've seen that all of our analysis tools to create a very similar type of report so that once you get familiar with one, you know how to do all of them. So that the common elements to all of our reports is that we generate a color-coded map based on the value that you're looking for. So in this case, you're looking for a thickness value. So this part will be colored according to the thickness that it has on the going on the color scale from one spectrum from one end of the spectrum to the other. That is going from red to blue, or from our or depending on the range, you could go from white to red. So in this case, it has chosen that the thicker part will be around the reddish tones, which is this, and that's I'm sorry, the other way around, the thinner parts, and the thicker ones will go towards the blue, going into the white. And you can see the color distribution in this model. If you want to see the specific thickness of a particular point, all you need to do is make sure that you have the measure from picking to enable here, and then you click on whatever you want to see, and that's going to give you the thickness at that particular point. So if you click around on areas of the same color, you're going to see that you get the same value. But if you click on an area of different color, you see that has a different value here, like this. It's almost twice as much. So let's see why. Oh, okay. That's because we have this boss coming out of the base surfaces. So obviously you have a bigger thickness, which is what you want in with a feature like this. We also have another mode, which is called segment mode, which is something that a lot of customer has been asking for. So instead of having a continuous color scale like we do right now, the segment mode will separate ranges of thickness into different bands, like an histogram. And let me enable that so you can see how it looks like. So all of the areas of a particular color, you know that they are within a certain range, and the range is indicated as well here. And you can, of course, move these ranges to as much as you want. You can change the number of segments that there are in the total scale. So instead of having maybe you want 5, maybe you want 7, or maybe you want 3, you can do that during creation time. Let's see if for some reason these colors do not fit your other applications, which might which might have the reverse order of colors. You can change that as well. So maybe you want white to represent your thinnest part, and you want red to represent your thicker part. You can do that easily. As with all of our other analysis tools, you can create an HTML report, and you can create a PDF report as well that you can use for sharing. And internally, you will always have an HTML report like this. This is a histogram of the thickness. So you can see where you have the most of your thickness will be around this band, which is around 25.92. So most of the thicknesses are in here. And then the distribution is below 2.59 is pretty much going downwards of linearly from there. And most of your thickness are around this area. Your average thickness is around this area. So you can get any information out of that table, of that histogram. Uh, let's see. Okay, I'm not going to explain some of the other filters here because they will be repeated in another tool that we'll be looking at next. So if it's to say this is the color map, you can see clearly the thickness, you can interrogate the model at any point. And something else that you can do in order to identify better the geometry and what's going on is just do a section cut. And you're gonna notice that when you click somewhere, you're gonna see leader lines showing from where to where we are measuring. So that's 4.492 from wall to wall for those two walls that are parallel. But if you do it in here, you're gonna see that it goes up all the way to this bump in here. So obviously that's a bigger or higher number. So that's that for the thickness checker. I'm gonna go over and talk about two tools that are used for modeling, draft and undercut analysis. So for those of you guys that work with molding operation, you know that when you design a mold, you gotta make sure that the piece can be ejected from that mold. So a draft angle is the angle between the mold, a mold piece, and your piece that you're molding. So you don't want those angles to be negative because that means that you won't be able to take your mold out of your part out of the mold. So let's start with the draft angles here. I've got an example that I can show you. So it's a small mold in here. So this has been designed properly, and you will see that these walls do have an angle between the flat face and the pulling direction. So incidentally, the pulling direction in here is perpendicular to this face. So that means that the part will be ejected in this direction, perpendicularly to that face. So that's why there is an angle between this face and the pulling direction. That will mean that the part will not get stuck. But if you want to make an analysis and see this in for a mode that you probably don't know, then you probably want to do this yourself. Right? So we're going to do a draft direction. So the first thing you do is that you select the body that represents your mode, then you select the face. So that represent the direction. There's a number of ways that you can select a direction. You can select a face, or you can specify with the coordinate system, or even you can just orient the part in that direction that you want, and then that will be your pulling direction. So we're gonna go ahead and run the analysis. Again, we have a color code, a color map, this histogram type of map, and you're gonna see that of course our irrelevant angle if the angle that is completely parallel to the pulling direction, perpendicular to the pulling direction, or parallel to our face, so that nothing can get stuck in that face because, well, it's the pulling direction. And as you deviate from the pulling direction into the direction of the face, you start getting material that might or might not get stuck depending on the angle. And here we know that we're good because all of these blue faces mean that we have a positive draft angle. Positive means as I look exactly towards this from the top, you see that there's an angle in here. So that means that you're not going to have a problem pulling the part. Yeah, actually, it might just uh, push out by itself once you turn this over because, well, the base is smaller and the top part is bigger. So by its own weight, it might just pull out by itself. So this is a very well-designed mode. You're not going to have any problems. But if you want to further get more information about your mode, which in this case might be relevant because it's a simple mode, but you can also get also get identify your negative draft angles, your max angle, your irrelevant angles, and so on. So again, as I said before, you can save this to a HTML report or a PDF report, and as you click around on your part, you also can interrogate it. So if you want to know the exact angle of a particular section, you click on it and it's going to tell it right away. So we have a positive 5 degrees angles. That's great. In here we have well, this stands for 0, which is a very, very low number. So that's 2.5 the exponent minus 0.006. So this is essentially 0. So this is an angle of 0, and that means that, well, you're not going to have a problem with this. But this is as far as you want to go. If you start going below 0, then you might get into trouble. So this is as the smallest angle that you can have, and anything above that is going to help you as long as you are as it keeps within well the tolerance of the material that you're building. So you don't want your material to use all over the place either. So that's the draft analysis. So let's go now into a very related type of analysis, which is the undercut analysis. So again, this is for molding operation, but the undercut will actually, as opposed to just giving you the angle and then you deciding what to do, the undercut will tell you the parts that they're actually producing geometry that will be not easy to eject because it will be behind a part of your mold. For example, in this mold here, you see that it's complex. It has many directions. So depending on the pulling direction that you choose, you might or might not have a problem. If we choose this pulling direction, that means that we're pulling this way. So probably most of it will eject without a problem, except maybe this area here because well there is an occluded undercut in there at some degree. You see that there is material above your part. So unless this mold is made out of silicone and you can flex it, you're gonna have a problem ejecting from this part. So maybe you would choose this direction instead. This direction seems like it doesn't create any trap material because it's mostly in the same direction in line with these areas in here. So that was probably the direction that was meant for pulling when this model was created. But who knows? Let's just do the analysis and that will tell us. So we go into the, this was the draft analysis. Now we're going to do the undercut analysis. So I'm no molding engineer, but I know a little bit about these operations. So first we select the body, then we select the pulling direction, which is going to be this one. And then we go ahead and create it. Again, we're getting a color map and we're getting mostly reds. And red doesn't necessarily mean bad. Red it just represents the direction of your core. So we have a very regular, very homogeneous color. So that means that we're probably okay choosing that direction. And of course, this will be the cavity direction. So you're not gonna be pulling from through the wall of the mold. So we don't care about that. And I don't see any undercuts identified, which will be gray. So this is a great direction for pulling out our piece out of the mold. You could go back and play with it, maybe choose a different direction. This time, maybe choose this face, and you will see how the colors change as you try on different directions, which are probably not in your best interest. So let's try that and see all of our colors will change because they will represent the areas where material may get trapped. So it's not as bad as I thought it would be. But then you do have undercut. This is an occluded undercut. You see the yellow area? That's the area that I was afraid might get trapped. So you can play around with it and find the best for you. Obviously, if you are designing this, you can design it in a way that it better suits you. But if you got this from a vendor and you need to evaluate it, this is how you do it. I'm going to touch, okay, we have 10 more minutes, so I'm going to touch on advanced geometry analysis and validation, which is something that we talked about before, but for those of you that were not here, I'm going to quickly touch on this. So this is a piece that we know has some problems. I'm going to enable the display of some of those issues that I know it has. So I know it has free edges and imprecision, so I'm going to do a quick check. And this is our basic type of check. We also have much more advanced check. I'm going to touch a bit on some of those. This is your most basic type of check. So it will determine that you have some problems with it. So far, these yellow ones are just imprecisions. So by that, I mean that the precision on how this face is joined to this other face, for example, you can see the interface here, they're not exact. As in fact, if you click both of these, you can see how there's a gap between them. So topologically speaking, they are connected. the software knows that this edge is supposed to be connected to this edge. But the way that these faces were made, they're not physically connected, they're not on top of each other, even though they should. So the software knows that and it detects that and reports that to you as being an imprecision. It's not really a problem because when you send this to other system or when you try to do operations with it, it's always going to try to keep these two edges together because it knows at that topology level, it knows that they go together. But this is not a perfect situation. So that's just up to you to decide if this is something that might hurt you because this gap will always exist in every system at every level. It will always exist. The difference is that the tolerance that you are allowing it to. So at this point I have a 0.01 millimeter tolerance. That means that this is bigger than that. If I make this bigger, this will go away. I gotta make it bigger. Let's see what's the tolerance level. Oh, so I need to make it bigger than 0.012. So let's just be safe and do 0.02. So it's gone away. Why? Because, well, it means that we don't care anymore because we're telling the system we don't care about anything smaller than 0.02. So don't mention that. So you see that that wasn't really a problem. It was more of a warning. So let's go back to how we were before, and now it's coming back. So with 3D evolution, there are tools to fix this, either automatically or manually. And I'm gonna turn off the display of imprecision now because I want to show you the free edges. So we can also detect the free edges, and let's run this check again so we can see where they are. So we have 9 free edges now. So in order to find them, we can use our filter. So we're gonna select to see only the bad faces. Okay, I see something in here. So this is actually a free edge because we have geometry that has a gap between edges like here. And I know there's a bigger one somewhere on the other side of the model. And we can actually choose to see where the errors are. So if you select this and you ask it to only show you those, we can do that as well. Let's see. We're not from this tool. Let's try another filter, open faces. Okay. So in here, and now that we identify where it is, I'm gonna bring up the geometry as it was before. So here we have a hole. This is the plain O hole. That means that the geometry that was in here was not correctly translated. Or maybe this used to fill the whole thing, but it got corrupted during translation. So it's just letting us know that between this edge and this edge, there is no connection, there is no surface at all, there's nothing. So we know we have a problem. So at this point in 3D evolution, you will heal it using the healing tool. Or in here, it helps you document it. So you can also create an HTML file or a 3D PDF file showing this, so you can send this back to your supplier or the producer of this file. So you tell them, hey, there's a problem, I need you to fix this. This is exactly where it is. And there are more advanced forms of analysis as well. I'm gonna go into our advanced check. So this actually goes deeper and interrogates the geometry at that topologic level. So let's go and find out the parts that have a twist to them. So I'm gonna select only those with a problem, and then I'm gonna say view alone because I want to look at them. So here's one. Obviously, there's something weird about it. You see how the surface goes beyond the edge. So let's analyze the control points. Probably, yeah, there are all over the place. Usually, for a good surface, the control points will be pretty close, or or in the best case, they will be right on top of your surface. In this case, you can see how bad they are. So we could repair this in 3D evolution. In Analyzer, we just use this to create a report and then document and then give this back to whoever produced this file. So this is a more advanced type of checking. And there are also some other different checks that are used in different contexts. And I'm going to get out of this mode and should go back to the displaying the whole thing. Maybe even use a different model for the example. So let me go back and see. Yeah. Okay, so I'm going to talk a little bit about Lothar. I think we have 6 more minutes, so I'm going to try to make this fast.
Right, and within those 6 minutes, if there are any comments, questions, requests, please let us know through either the Q&A function or chat.
Yeah, feel free to stop me at any point. I'm going to keep on explaining this. And if you want me to go back and get more specific on a particular thing, or you have a question, just raise your hand and put it in the chat window. Okay, so Lothar. Lothar is a standard that stands for long-term archival and retrieval. So that means that the files we create today, we should be make which we should ensure that these are available and we can open this in 10, 15 years, not like we did before, because now that's part of the problems that we have now in the industry. The files that were created 20, 30, 50 years ago are very hard for companies that have been around that long, are very hard to now handle, because well, no measures were taken then to ensure compatibility in the future. So now, if we do everything according to this Lothar standard, that means that whatever we create today, we'll be able to open it up in the future. And one of the recommendations or the procedures that it has is applying the GBP validation. GBP stands for graph geometric validation properties. I'm going to show you what that is. So when you create a step file that is compliant with Lothar, and it's a step 242 type or release level, that means that that file was created with the validation properties embedded into it. These validation properties are for GBP, though there can be many things. That the most basic will be your area, your surface area, your volume, maybe your mass, your centroid. So for example, let's take this file and let's say that this was a Creo, a CATIA, or a native file. I'm going to convert this to step 242 and I want it to go with GBP properties. So that means that right before saving, the system will calculate those mass properties. Those will be saved into the model as metadata, and then the model will be converted and saved. So next time I bring it in like I'm doing now, I can just run a validation, and the validation will look at those values that were stored before, and then we will calculate those again based on the geometry that we see, and then compare them. And I need to go into my edit profile. I'm going to show you how to create your custom profile. So you create one that's called GBP, and you make sure that you're only including the checks that are related to GBP. So I'm looking through all of these different categories. So you see what we have for checking, and then going back into validation. So only the geometric validation properties will be enabled. So I want volume, I want area, and I want centroid to be checked. I know I don't have any PMI in here, and it's not a tessellated file, it's not a composite file, and it's not an assembly. So I'm just going to use volume, area, and centroid. So with 3 minutes to go, I'm going to run this. Hopefully, hopefully it's a good example. Okay, so yeah, it's a good example because it fails out 3 checks. So I'm going to show you the report. So it failed by just a little bit, but it's above our threshold. So in this case, our threshold was smaller than this. So that means that this small difference is a problem for us. And this can actually be a practical use case, like in the manufacturing of turbine fins, turbine blades. This has to be very, very, very precise. So this will be a problem in those cases. So in this case, you see that this here are the data that was saved as metadata into the part when it was created. This is what we can check now, and when we compare those, we have a difference. So this is why this is failing the validation. So as you notice, we don't have to keep track of the original one in order to validate this derived part. So that's one of the advantage of the loader process described. And so now when you see GBP, you know that this is what it means. It's a way to stay compliant with loader, and it's a way that your files can be uh, self-validated in the future. And that's something fully implemented into 3D Evolution and 3D Analyzer, as you're seeing.